Welcome back to the second video in which I discuss the rough idea of the proof of our theorem about the absence of non-trivial local conserved quantities. But before that, I have to change the title. First of all, I forgot to say this is spin 1/2. And in our paper, we discuss XY and XYZ model. But in this video, for simplicity, I just consider something called XX model. Okay. And in two-dimension. Well, doing three or higher dimension is just trivial, but this makes some equations and discussion simpler. Okay. Let's get started with model and main result. So lambda is just a square lattice with L by L squared sides, and I take periodic boundary condition. By B, I denote the pair, I denote the set of pairs of nearest neighbor sites, like this. Okay, and then X, U, Y, U, Z, U denote copies of the Pauli matrices on sites U, and this is the Hamiltonian for the XX model on spin 1/2. It's simply the sum of XX plus YY interaction. Sometimes people refer to this as XY model, but in this case, so we have coefficient 1 for both XX and YY. So to emphasize this, sometimes people call this the XX model. Okay. Now, this is my boldface A, and this denotes the product of Pauli. That's a simple tensor product of Pauli matrices. Okay, and this S, which is the support of A, is just a non-empty subset of lambda. Okay, and I denote by P the set of all products like this. And then I also define the width of A by looking at the span of its support. So if you want to define the horizontal width, you simply, so here's the empty site, but you don't care about this, and you simply count the number of sites in this span, and it's 5. And as for vertical direction, it's 2. And just width of A is the maximum of these two. So in this case, width is 5. Okay. Right. So I'll discuss local conserved quantity. So first, we fix this constant K max, which gives the maximum width, and it is in the range between 3 and L over 2. Okay. And this is the candidate of local conserved quantity. It's simply a linear combination of all these products with arbitrary complex coefficients. And we make no symmetry assumptions for QA, like translation symmetry or rotation symmetry or anything. These are just arbitrary. Okay. And here is a constraint about the width. We allow all products, but whose width does not exceed K max. And we also assume that this is sort of saturated in the sense that there must be some A with non-zero coefficient which has this maximum width. That's the assumption. This is the candidate for local conserved quantity, and we say that Q is a local conserved quantity if it commutes with the Hamiltonian. And the theorem said that there is no such Q. How do you prove this kind of theorem, or how did Naoto Shiraishi prove this for the first time in 2019 for the one-dimensional system? Well, the basic strategy is very, very simple. So Q is a candidate of local conserved quantity, but forget about this and just consider an operator of this form, general operator of this form, and then take a commutator with Hamiltonian, you know this form. So if you know the commutation relations between the Pauli matrices, you can just compute the result, this commutator, and expand it in terms of all these products. It can be always expanded, and you get this unique coefficient, which is, of course, a linear combination of QA. Okay? And then this condition 2 about local conserved quantity is becomes this. Because if you set this equals 0, then all these are independent. Each coefficient must be 0. So you get CB equals 0 for all B. And since CB is a linear combination of QA, you get a coupled linear equations for these QA. Okay. And then what you want to do is to use sort of high school mathematics to analyze these couple linear equations to conclude that for any A with its K max, QA must be 0. Well, but this contradicts with this assumption about the K max, so this proves the theorem. Okay, so this is a very simple strategy, and it's very hard to imagine that this kind of simple strategy works for this kind of quantum many-body system, but Naoto back in 2019 showed that it really works. Okay, so we apply this strategy to a higher dimensional problem. Okay, now let's look at this commutation things more carefully. So suppose let this lowercase h be a part of Hamiltonian. This is a product and which is a part of Hamiltonian. So in this case, it's simply xx or yy. Okay. And take any product A and look at the commutator between h and a. Okay. Then I say that this commutator may be either 0 or have this form with some b. Okay, it's plus minus 2i times b. B is some product. Okay, you will, well, this is easy, and you will see the example soon in the next page. Okay, but anyway, believe me this. Okay, so if this number 2 is the case with some h, a piece of Hamiltonian h, then we say that b is generated by a. So we repeatedly use this terminology here in this video and also in our paper. Okay. All right, so this is the terminology, and here comes a very important basic observation. Take any product B and list all A's that generate B and also have width less than or equal to K max. Okay. And then I claim that this CB, what is CB? Well, CB is this coefficient. You take the commutator between H and Q and, okay, and expand it in B. This CB is written like this because, in order for, if you want to compute this, then you just plug in here. So this is simply expanded in terms of sum over A, QA, and here comes H and A. So this commutation relation is important. And again, H is sum of small h. Okay, basically the sum of small h. So what you want to do is to consider this for all possible h and a, and this is a result. Okay, this is a result. So this CB, if B is generated only by these guys, then this CB equals 2i, comes from here, and plus minus, we don't, I mean, if you know the details of these products, you know whether it's plus or minus, but I don't care for the moment, so it's either plus or minus, and this is CB. And now, if this condition is equivalent to this, so a sufficient condition that Q is a local conserved quantity is this. All right, so we have this, and this is just the sum over j from 1 to n. But if n is 1, this is very meaningful. Okay, if n is 1, there's only one term, and you say it's 0. So we know this. Okay, so we learned by setting n equal 1 here that if there is b such that a is the only product with width smaller than k max, less than or equal to k max, that generates b, then this coefficient must be 0. This is very good information. And if you set n equal 2, then you have two a's, and if you sort of sum them, and you get 0. So what do you get for n equal 2 is this. This is again also very important. If there's b such that a and a prime are the only products with this condition that generate b, then the coefficients of these two guys must be related like this. Of course, you can again compute this plus minus sign. We do it later, but for the moment, this is enough. Okay, this is a very simple but important observation. So let's look at this commutation relation more carefully. So I only look at two examples, but it's enough. I mean, these are enough to understand the general situation. Okay, so suppose that this is my A. Okay, so these are just Pauli matrices, and this is arranged in this two-dimensional square lattice like this. Okay, and I will take the commutator of the piece of Hamiltonian XX and A. And of course, if these two guys are separated far away, then of course they commute with each other. There must be some overlap. And in this case, I hope you understand the situation. So here are sites U, V, and I assume that this site V overlap. Okay. And then if I take this commutator, I argue that it becomes like this. You get a new product like this and this coefficient 2i. Why? Well, this is kind of easy because, well, we have a bunch of operators, but Pauli matrices, but you can forget about this because, I mean, there's only overlap here. So the basic thing you want to consider is the commutator between XU, XV, this is a part of Hamiltonian, and YV. But of course you can, this XU is only here, so you can just pull it out. And then what you want to consider is simply the commutator between X and Y. And of course you know this. And then this becomes 2i next dx. And one very important point here is that if you compare the support of B and support of A, this one is strictly larger because this one. Okay, U was empty here, but empty means we had identity here. But anyway, if you have here it was empty and we have X. Okay, and this is very, very important. It's so important that we make it. We define a new symbol. Okay? And I hope this is understandable. This says this represents a relation between A and B. This says that B is obtained. B is generated from A by appending X here at new site U. Okay, so this shows that U is a new site. This is an appended site, and which is attached, which is neighboring to V. Okay, V was already in the support of A, and XX shows that we take commutator with XX. Is this clear? Okay, so again, we make use of this symbol repeatedly in this video and also in our paper. Okay, so this is the most important case, and this is less important case. Suppose that now it's overlapping like this, and so we have same y here and different things here. In this case, you see that here's 2y, so y squared is 1. So this sort of vanishes, and you only consider the commutation relation between yx, and you get this. So in this case, this is our B, and so you have identity here. So in this case, the support of B is strictly smaller than support of A. And actually, these processes exist, but we don't have to look at them too carefully. That you will find out why. And these are the cases where the supports of this and this overlap, but we have zero commutators. And this is just simple. This is XX and XX. The commutator of yourself is just 0, so you get 0. This is less trivial, but if you have these are different, these guys are different, then if you use the basic relations of Pauli matrices, then you find that this is 0. It's an easy exercise. All right, so to sum, you only have to consider these two cases, and this case in which B is obtained by appending site U to A is most important. Okay, now let me state a non-trivial statement, which I call monogamy lemma. Okay, and now take any product with whose width is Kmax. But now this means that the horizontal width or the vertical width is Kmax. So without loss of generality, let's suppose that it's a horizontal width. So we assume that width 1, the horizontal width of A is Kmax. And then it looks like this, right? So this is K. Oh, of course, we live in a big lattice. So this is a very small portion. So you don't have to care about periodic boundary condition here. The boundary is far, far away. So then you can, by looking at this, you know what I mean. You can define leftmost sites in support of A, and also rightmost sites. In this case, there's only one, but rightmost sites of Kmax, of support A. Okay, and then here's a lemma. This is a product with this horizontal width Kmax, and it has a non-unique leftmost sites or non-unique rightmost site. Then the coefficient must be 0. How do you prove this? Without loss of generality, suppose that leftmost sites are not unique. And then let's call this, and let's say that X is a rightmost site, and y prime are distinct leftmost sides. And then you take this A and consider this new product. I use this appending symbol now. So here, this is X, this is the rightmost side, and then you append new site X plus 1, 0 to the right to get this. Now, this had width K max, the horizontal width K max, so this new B has horizontal width K max plus 1. Now, I argue that this A is the only product with this condition that generates B. Why? Well, you ask what A prime can generate this. I mean, looking at this, to find that you just sort of eliminate one of these sites from support to find A prime. But the condition is that it must have horizontal width K max or less. Then you have to reduce the width. But the only way you can reduce the width of this is to eliminate this, but you go back to this original A, right? If you may think about eliminating this side, but it doesn't reduce the width. Okay, the same for this, or same for any side. Okay, so the only way to reduce the width of this thing is to eliminate this, which gives you just back to A. So this says that A is the only product with this condition that generates B. Then if you go back to page 3, and if you look at this, then you find that this coefficient must be 0. Okay. So this lemma, of course, we did never encounter this kind of thing in one-dimensional case. This is characteristic for 2 or higher dimensional systems. Okay. Now I'm ready to define a procedure that I call the Shiraishi shift. Okay, take any product A and suppose that the horizontal width is K max. And I want to consider the situation which is not covered by this lemma. So I will assume that A has a unique leftmost side Y and a unique rightmost side X. Okay, and I will define the shift. First of all, I do the same thing as before. So this is our A, and then this is the rightmost side X. Then I will append WW here. In this case, I will append XX here, and then X is here, and you take the commutation relation between X and Z, you get Y. Okay. I think now you are more used to this. So you get this. And now you have horizontal width K max plus 1. And I have to, and here's my convention for choosing W. Okay. When AX, this target site has Y or Z, I choose W to be X. This is just a convention. You can put Z here, but anyway, this is my convention. And then if this target is X, then I choose W to be Y. So this convention just makes this procedure unique. And then this is okay. Then you ask if there's any A prime which generates B like this. And this says that B is generated from A prime by appending Y. Okay, so this is A prime. Okay? It has width K max. It has smaller width than B. And this B is obtained by this appending site Y here. So in this case, if you take commutator with XX, then this X is appended and this Y changes to Z, and you precisely get this. Okay. So in this case, in this case, A prime existed. Okay. And W prime could be X or Y. And then I say that if A prime exists, then it is unique. You can find it from this, examining this situation carefully. And also, of course, it has with this horizontal width K max. Okay, so if this kind of A prime exists, then I call it the Shiraishi shift of A and denote it as SA. S stands for Shiraishi, or the shift. Okay. And if there's no such A prime, of course, there can be situation that you have never no such A prime, and then we say that the shift, Shiraishi shift, does not exist. Okay, this clear? And here's a very important property of the Shiraishi shift, and So let's recall this 6, 5, and 6 in page 3. Page 3. Okay. In page 3, we saw that if there's some B and A is the only product that generates B, then A equals 0. And if there's some B and A prime are the only products that generate B, then they are related like this. Okay. Then we use this relation to the shift case. If first of all, if the Shiraishi shift of A does not exist, then A is the only product with this condition that generates B. And then from this 5, you see that this has 0 coefficient. Okay. If you cannot Shiraishi shift, then its coefficient is 0. Very simple. Oops. And then this one, if the Shiraishi shift A prime exists, then A and A prime are the only products with this condition that generates B. You can easily convince yourself by looking at this, and you can of course prove it. And then in this case, this relation 6 tells you that the coefficients are related. And again, you can find out this sign, and we do in later, but now I don't care. Okay, so they are related like this. Okay, then these are basic observation, and these are corollaries. So if you use this repeatedly, then this Sn of A is simply the repeated shift, n-fold shift. And then, of course, any QA and the coefficient of its n shift are related by this. And also, we have this. So suppose that if you consider shift, and you could shift for a while, but you find at some end that SNA does not exist. Then this shows that Q of Q of Sn minus 1A is 0. So by using this again, you see that this QA is 0. Very useful. Okay. Now, here's the basic theorem. I say lemma. Here's a basic lemma about the shiftability of a product. So let's take a product and suppose that its horizontal width is k max. Then we say that the nth Shiraishi shift of A exists for n greater than or equal to k max exists if and only if A is a product of k max Pauli matrices on a straight line. First of all, so we are considering two-dimensional problem, but we say that in order for this to be shiftable, all the product operator must align horizontally. Okay? And also we know the form precisely. It must have this form. Okay, so we have a bunch of z's in the middle, and at the two ends we may have x or y. Okay, so let's prove this, and instead of writing down the formal proof, sorry, I will look at some examples, but I think these are just convincing. So let's consider the case with k max equal 5, 1, 2, 3, 4, 5. This is our A, and this is in this standard correct form. Okay, in this case, I chose both them to be x. And then this has k max, and then I append y to the right. So that means I take the commutator between y, and then this y comes here, and you take commutator between y and x, and then becomes z. This is very important. Okay, so we had x, but this changed into b, and we have y here. Okay, so this is a longer one. This has width 6, so we have to shorten this, and then you find that whether you can generate this by some other product. Yes, you can. This is another product with Kmax width 5, and if you take commutator between xx here, then this becomes x, and then you take commutator between x and y, and you get z, right? So this is the first Shiraishi shift of this thing, and the rest is basically the same. You take the commutator between xx, and then this becomes x, and again this becomes z. And this is a longer one with width 6, and you want to shorten this, you get this. From this, you can generate this. So this is a second Shiraishi shift, but you return to the same thing, just shift it by 2 lattice sites, and you're sure that you can repeat this forever. Okay, so this shows that if A is of this form, you can Shiraishi shift for this forever. And of course, if this is y, you can do the same thing. If this is y, you can do the same thing, you know. So the proof works for any of this thing. Okay, so this is a case where something can be shifted forever. These are the cases where you cannot shift forever, and these are very simple. So suppose that, I mean, products are not aligned in one direction on a single line. So you have something like this. And then in this case, again, you have you have 6 Pauli matrices, but you know, in this case, the horizontal width is 5. 1, 2, 3, 4, 5. Okay. And then you append x here to get this. And then this is generated by this. Okay. So this is a first Shiraishi shift. That is okay. Then, but you can never shift this, right? Because I mean, you can, of course, append this. You can always append this. But can you eliminate this? No. No. In this case, you have 2 leftmost sides. So this, in this case, the second Shiraishi shift does not exist. And this is much more trivial. So suppose that you have an empty site. Of course, you have identity here. Suppose you have an empty site here, and then you once Shiraishi shift, you get this. But you know, you can never eliminate this, right? Yeah, you can. No. I want to say, okay, you can never eliminate this. You want to have a product with this Kmax. So you want to have something which lives here, but you can never get it. Okay. So this in this case too, the second Shiraishi shift does not exist. These are just trivial case. This is less trivial case. You have to be careful. I said that in order for a product to be shiftable, it must have only z's in the middle, except for this leftmost and rightmost thing. And you have seen that it really works. And I think you are looking, you have already seen the trick. Whenever you add something, you know, here you added yy, but you got z. Okay? Here you added xx, but you got z. Whenever you add xx or yy to the right, you produce z. That is one key. Okay, so let's look at this example, which is not in this standard form. I mean, these are not these. And okay, you do the same thing, and this is the first Shiraishi shift. That is okay. And then you do this, and this is a second Shiraishi shift. Oops, I'm sorry, I didn't write it down. This is where. Yes, the second Shiraishi shift does exist again. And then you append this, and then you want to eliminate this to get this by taking commutation relation. But no, you cannot do that. No, what I'm saying. Yes. You want to eliminate this. So you want to have something here, and this something should give this by taking commutator. But you know, in order to have z here, you have to take commutator with zz, but that is not allowed in our case of XX model. Okay, in the XYZ model, the situation is slightly different. But so here it stops. Okay, so this the third Shiraishi shift does not exist in this case. So what do you learn from this? Here you found that you cannot have z at the left end. Of course, at the end. But this means, why did we have z at the end? Well, if you recall this process, you will see that if you all have z's here, then you never get z here, because if you know, this is again, you can learn from here. You had a whole bunch of z's. So whenever you eliminate this, you get something which is not, because you know, you eliminate this by taking x commutator with xx. So you get something other than z, right? Of course. And here, again, you try to eliminate this, you get here something other than z. Okay. So if you have a bunch of z's inside, you're always guaranteed that you won't get z at the leftmost side. In this case, you had something other than z, and this resulted in this z at the leftmost side. Okay, so this is what we learned. And also, I don't demonstrate this, but you can't, if you have z at the right hand, that is that is of course allowed, but if you then do a single shift to this thing, you will find X or Y inside. You will easily find this. Okay. And then you cannot have Z at the right hand. Okay, so by putting all this together, you will convince yourself that the only thing you can have is that these in the middle and X or Y here. Okay, this was an informal proof, but I think I have explained the essence of the proof of this important lemma. Okay, so let's repeat this lemma. You have product A whose horizontal weighted is K max, the maximum weighted, then the n-fold Shiraishi shift with this exists if and only if A is a product on a single line with this precise form. Okay. And we know that if SNA does not exist, then QA equals 0, that we discussed in page 7. So now our game becomes slightly easier. Suppose that we have a product whose horizontal width is K max. Then we know from this that QA is 0 unless A is this standard form. Okay. So there could be many varieties of A's with many different shapes, but if it is not of this form, we know that its coefficient is 0. Okay, then what we want to do is to take this standard form, so there are 4 possibilities, and prove that the coefficient is 0. Then we see that for any A with this horizontal width K max, this coefficient is 0. But of course this contradicts with our assumption about K max, and this proves our theorem. Okay. So the only thing we want to do is to solve this one-dimensional problem. Okay, I mean, not really one-dimensional. I mean, sort of close to one-dimensional problem. Here, this product is sort of one-dimensional. It's only aligned in one direction. Okay, so this was the first half of the proof. In the second half, we solve this one-dimensional puzzle. And it's a bit technical. This second half is a bit technical, and we have to choose precise products and write down condition and show that the coefficient must be 0. Okay, so I will only discuss the case K max equals 3 in detail and leave the general case to our paper. Okay, but I would say that this K max equals 3 case contains some essence of the proof. Of course, but I'm sure that you don't believe me. I mean, you always define in textbook that in this simplest case covers the general idea, but if you try to do the general case, it's much harder. But it's always the case. But anyway, essence is here. Okay, so let's consider. So we are in 2 dimension. So this, if K max equals 3, this is one of the standard form. Okay, the standard form is that you have X or Y at the leftmost or the rightmost side, and you have bunch of Z's. But in this case, K max equals 3, you don't have bunch. You only have one Z in middle. But so this is the standard form. Okay, and we want to show that QC1 equals 0. And for this purpose, so anyway, this is K max equals 3, so this has with a 3. For this purpose, we define these products here. Okay, so this one is really basic. If you append YY here, then this becomes this. Okay, and this is E2. This has only width 2. This still has width 3. Okay, so this is different than B's that we considered. It has larger widths, but this has the same widths, and also we consider this. And then you find if you look at this, and you find that D1 is generated by these 3 guys through these appending operations. And now I declare this target operator to make things clear. So in this case, this says that D1 is obtained from C1 by appending YY and from adding new thing at 6 and target site is 2. Okay, we'll see. And these are the same thing, 1, 2 here. And in this case, 2, 1. And these are, okay, all right. So D1 is generated by C1, E2, C1 prime. And these are the only operators. These three are the only products that generates D1 through this appending operation. But there are other products with larger support than D1. Okay, if you remember, I'm sorry for going back. No, yeah, okay. So I was the appending operation corresponding to this example 1, but there are situations corresponding to this example 2, in which case the support of B is strictly less than support of A. It's okay. So was sorry, I can't do this in a clever manner, but okay. So there are other products that have larger support than D1, and by taking commutator, it sort of shrinks and becomes D1. So there are a bunch of operators, products that I won't write down. But anyway, so let's recall this setting. So this is a candidate for local conserved quantity, and this coefficient CB is defined this way. So now, if I compute the coefficient CD1, I have to consider all products that generates D1. So in this case, we have QC1, QE2, and if you consider this here, you find the sign, you don't have to care. And also you have this bunch of operator products with larger support than D1. But I claim that all these guys have zero coefficients. Why do you know this? Well, because, so let's look at this C1 double prime. So C1 double prime is this. C1 double prime is this one. It has horizontal width 3. So this is K max. So you cannot still exclude this, but look at this. It has width 3, or actually it has width K max equals 3, but it's not in a straight form. Let's look at this lemma. If A has horizontal width K max, and then its coefficient is 0, unless it is aligned in a straight line. Okay? So this is not aligned in a straight line, so you see that this guy have 0 coefficient. And for the same reason, D1 has width 3, but again, width 2 in this direction. It's not aligned on a straight line. And if you add something new, of course, it gets worse. So all these guys have 0 coefficient. This is a very good news. And whoa, how about this thing? This is not aligned on a straight line. So does this have 0 coefficient? Well, you cannot, it has 0 coefficient, but you can still not conclude, because in this case, it has width 2. Okay. So this lemma applies only to width K max, horizontal width K max of products. So in this case, it has width 2 in both directions. So this is not excluded by the lemma yet. So you don't have to consider this thing. So by this condition, this is a sufficient condition that Q is a local conserved quantity. This is 0, so you get this condition. So one condition. Of course, this is not yet sufficient to conclude that QC1 is 0, so you consider further products. So this is C2. This is something that I call C2, but this is just a shift, Shiraishi shift of this thing. Okay, you append YY here, and you eliminate this, and you get this. Okay, so this is again in the standard form, and this is D2. So if you compare D1 and D2, this is interesting. So we appended Y here at this site. And this is actually the same site. And it's appended here, but everything is shifted on the right. And this is E2 we already know, and this is new F1. And again, you see that this D2 is generated by this C2 and good old E2 like this in appending operation. And of course, there are several other products that generate D2, but you don't have to consider that for the same reason, like here. And so from this, you find that this CD2 is written like this, and from this you get this condition. One more, we need one more condition, and you consider this F1, and this is something we already did, but you see that F1 is generated by this C1 and C2 like this. Well, this is something we already considered in this shift case. Oh, probably this should be called B1. I'm sorry. Yeah, I don't have to be sorry, but this should better be called B1. Please call this B1. And then this tells you that this C of B, no, B1. Oops, there were several mistakes. So let's pause. Okay, so it's been corrected. So yes, so B1 is generated like this, like before. And from this, now I compute the sign carefully to get this, to find that this CB1 is 0. CB1 is like this, and since this must be 0, this must be 0, you get this third condition. Okay, so you get this 5 and this and this. You put them together. This is what we have found. And then now you use your junior high school mathematics to solve this coupled equation to find that QC1 and QC2 are 0. Oh, and of course, QE2 is also 0, but we're not interested in this. Okay. And C1 is YZX, C2 is XZY. Okay. So this covered the 2 of the 4 standard forms. The rest is much easier. If you look at this XZX, and then you only need to consider this D1 prime. And then in this case, D1 prime is generated by this, but this is the only thing you have to consider. And then you immediately get this. And this is the second, this is another standard form. But again, you do the same thing like here. To here we related this C1 and C2, but in terms of this. So here you can relate this and this by considering another B1 prime, which has horizontal with this 4 to get this. Okay, this is another easy exercise. Okay, so by this, we get this and we get this, and we are done. Okay, we have shown that this is the case for k max equals 3. So the k max 3 case is done. So okay, so if you're satisfied with k max equals 3, you have learned the complete proof of the absence of local conserved quantity. And of course, we have to go to general case with k max greater than equal to 3. And then for this, you have to find a pattern out of this. So the basic pattern was that this is what you want to consider, and then you appended something here to make this kind of a non-straight thing. And then you consider the shift of both things, okay? And then you also needed this E, but by combining this, you get a sufficient set of coupled equations. So what you want to do is here, okay? So in this case, J runs from 1 to, you have to consider a bunch of CJs, and it has this kind of form. And again, you consider a bunch of Ds and a bunch of Bs and some exceptional case and so on. And you just write down the set of coupled equation and so on. And you anyway reach the conclusion. Of course, it's complicated, and you have to take care of some exceptional cases. I won't say that easy. This is easy, but anyway, it's straightforward to do, and the essence is contained in k max equals 3 case. Okay, so that's all what I wanted to say, talk about in this video. So, well, thank you very much for watching this complicated video, and well, see you again. Goodbye.